Hello students, welcome. So today we are going to start a new unit called solutions. So in this unit, as the name suggests, we are going to discuss about the solutions, their properties, different type of solutions, measurements of the solution, that means concentrations in different ways, and factor affecting solutions. So first let's start with unit objectives. First, describe the formation of different type of solutions. Second, express the concentration of solution in different units. Next, state and explain Henry's law and Raoult's law. Distinguish between ideal and non-ideal solution. Explain deviations of real solutions from Raoult's law. Describe the colligative properties of the solution and correlate these with the molar masses of the solution, and explain abnormal colligative properties exhibited by some solutes in solution. Almost all the processes in body occurs in some kind of liquid solution. So from that line we can understand the importance of the solutions. Almost every reaction occurring inside the body uses solution as a medium for the reaction. And you also notice that in laboratory, majority laboratory chemicals react in solution form. That means we usually do not mix two different solids. Suppose we have two different powders of two different chemicals and we mix it and you will get product. These type of reactions usually do not occur. First we have to make them solutions and then they can react with each other easily and quickly. So majority in laboratory we will use solution medium for the reaction. In normal life we rarely come across pure substances. Most of these are mixtures containing two or more pure substances. Their utility or importance in the life depends on their composition. Now, as for example, we can take the example of drinking water. Our drinking water is not pure water. It is mixture of different type of chemicals, usually salts. And these salts are necessary for our body, and that's why they are referred as minerals and we call it mineral water. Now, as mentioned, for example, the properties of brass, mixture of copper and zinc, are quite different from those of German silver, mixture of copper and zinc and nickel, or bronze, mixture of copper and tin. 1 part per million ppm of fluoride ions in water prevents tooth decay, while 1.5 ppm causes the tooth to become mottle. That means spots will appear on teeth, and high concentration of fluoride ions can be poisonous. For example, sodium fluoride is used in rat poison. Intravenous injections are always dissolved in water containing salt at particular ionic concentration that matches with the blood plasma concentrations, and so on. And this last explanation is related with our very last topic of the unit, osmotic pressure. We will discuss about it in that point. So in this unit we will consider mostly liquid solutions and their formations. This will be followed by the studying the properties of the solution like vapor pressure and colligative properties. We will begin with the type of solution and then various alternatives in which concentrations of solution can be expressed in liquid solution. So our first point start with type of solutions. Solutions are homogeneous mixture of two or more than two components. By homogeneous mixture, it means its composition and properties are uniform throughout the mixture. That means upper part of the solution has same type of properties as the lower part of solution. Generally, the compound that are present in largest quantity is known as solvent, and solvent determines the physical state in which solution exists. That means higher quantity of component or compound is known as solvent, and physical state of solvent is the physical state of solution. One or more component present in the solution other than the solvents are called solutes. So lower quantity compounds are called solutes and higher quantity compound are called solvents. In this unit we shall consider only binary solution, that is which contains only two different compounds. One will be solute, one will be solvent. And here each component may be solid, liquid or in gaseous state and are summarized in table 2.1. So according to physical state, here we have main three different type of solutions: gaseous, liquid and solid. So as mentioned earlier, higher quantity will decide the physical state of solution, and higher quantity, that means quantity of solvent. So solvent will decide the nature of solution. So in case of gaseous solution, all the solvents are in gaseous state. In liquid solution, all of them, that means solvents, are in liquid state, and in solid solutions we have solid solvents. And solutes may vary either in gas, liquid or solid. So that means we have total 9 different type of possibilities: gas gas solution, gas liquid, solid gas, gas liquid, liquid liquid, solid liquid, gas solid, liquid solid, and solid solid. So we have total 9 possibilities of different type of combinations, and mainly 3 different type of solutions: gaseous, liquid, and solid solution, and all of them with their examples are mentioned here. Next point, expressing concentration of solutions. So we know that we have some methods to express the concentration. We are familiar with it. We are going to learn them again: molarity, molality, etc. Composition of the solution can be described by expressing its concentration. The latter can be expressed either quantitatively or qualitatively. For example, qualitatively we can say that the solution is dilute, that is a relatively very small quantity of solute, or it is concentrated, that means it has very large quantity of solute. But in real life these kind of descriptions can add to a lot of confusion, and thus need quantitative description for the solution. That means we need some numbers which represents two different solutions, or we can compare it. As for example, suppose we have two different dilute solutions. Okay, so solution A and solution B, qualitatively both of them are dilute, but which of them is more dilute or which of them is less dilute? Let's say first solution contains 1 gram of solute and second contains 1.5 grams of solute. So obviously higher quantity of solute, it is comparatively less dilute, or it has higher concentration. So we need some specific numbers which can be compared with each other. So there are several ways by which we can describe the concentrations of the solution quantitatively, and first is mass percentage, that means weight by weight. So mass percentage of the solute inside the solution is known as mass percentage, or mass weight by weight percent. So simple calculation, all you need is the mass of the solute divided by total mass of the solution multiplied by 100. For example, as mentioned here, we have 10% glucose in water by mass. It represents, suppose we have 100 grams of solution, then 10% of that mass, that means 10 gram will be the glucose and 90 grams will be water. So we have 10 gram glucose and 90 gram of our solute H2O. And with the same relationship, we can even find the mass of the solute in different scenario. As for example, suppose we have 10% 200 grams of the same solution. That means 10% glucose solution having 200 grams of mass. So what will be the mass of the glucose in it? So direct answer will be 20 grams, but still we can find it from cross multiplication. If it says it is 10% solution, that means 100 gram contains 10 gram, then given quantity, that means 200 grams contains how many grams? So cross multiplication, 200 multiplied by 10 divided by 100, it is equal to 20 grams. So that's how we can find the values. Concentration described by the mass percentage is commonly used in industrial chemical applications. For example, commercial bleaching solution contains 3.62 mass percentage of sodium hypochlorite in water. That means we have 3.62 grams of sodium hypochlorite in total 100 grams of solution. Second method is volume percentage, volume by volume. Again, it is same type, but instead of mass, we are using volume of the solution. So volume of component or solute divided by total volume multiplied by 100 is equal to volume percentage of the component. And for example, 10% ethanol solution in water by volume, it represents we have 10 ml of the ethanol and 90 ml of water. That means if we have total 100 ml solution, then 10% of that total volume, 10 ml, is belongs to ethanol, and remaining 90%, that means 90 ml, belongs to water. Similarly, just like the previous case, we can find the quantity of the solute by placing the cross multiplication. Solution containing liquids are commonly expressed in this unit. For example, 35% volume by volume solution of the ethylene glycol, an antifreeze. It is used in car for cooling the engine. At this concentration, the antifreeze lowers the freezing point of water to 255.4 Kelvin or minus 17.6 degrees Celsius. We are going to discuss about this topic as well in upcoming points, how we can decrease the freezing points of the liquids. Third one is mass by volume. That means mass of solute divided by volume of the solution multiplied by 100. That means value of solute will be taken in grams and value of solution will be taken in milliliters or liters depending on the requirement. So another unit which is commonly used in medicine and pharmacy is mass by volume percentage. It is the mass of solute dissolved in 100 ml of the solution. Now next one is a bit important, part per million. When a solution is present in trace quantity, that means very minor quantity, it is convenient to express the concentration in part per million or ppm. Now million, that means 10 lakhs. So simply we can say that part of our solute per million part, that means per 10 lakh of the total particles, number of particles of our solute is known as ppm of the solute. So as the equation suggests, part per million is equal to number of part of the component, that means usually our solute, divided by total number of parts of all the components of the solution multiplied by 10 raised to 6, because we are finding parts per million. So 10 raised to 6 represents million. As in the case of percentage, concentration is part per million can also be expressed as mass to mass, volume to volume, and mass to volume. That means simply in percentage we took total is equal to 100, and here we will take total is equal to million. A liter of seawater which weighs 1030 grams contains about 6 into 10 raised to minus 3 grams of dissolved oxygen. So as we can see, the quantity of gas inside the solutions are very low. So if we check the concentration of total, which is mass of total, which is 1030 grams, and if we compare the quantity of oxygen in it, then it is quite very low, 6 into 10 raised to minus 3 grams, which is 0.006 grams. If we compare it with the total volume, which is 1030 grams, which is very greater than the quantity of oxygen in the same solution. So because of very low quantity, we have to measure it into ppm. Other methods are comparatively useless for this. If we convert this into percentage, then you will get very low value. That's why we need ppm unit. So such a small concentration is also expressed as 5.8 grams per 10 raised to 6 grams of the solution, which represents 5.8 ppm. Okay, parts of the solute, that means our oxygen, is 5.8 per 1 million of the solution or total components or particles. The seawater, the concentration of pollutants in the water or atmosphere are often expressed in this term and microgram per milliliter or ppm. Remaining points or concentration points will be discussed in next lecture.